So let's get to our program today. We have Historical Masonry, the Art and Science of Arches. This is our program description, as well as our learning objectives. You will have 1.0 professional development hours for the Masonry Institute and 1.0 hours for AIA Learning Unit, HSW. Our provider statement as required. All the certificates will be sent to everyone attending today, straight from myself. And today our giveaways are 2 of the Historic Construction and Conservation books as recommended by David Biggs. There will be a plastic box coming around. You'll put your name or business card within that. We'll pull for winners at the end. And our sponsor today is Leonard Masonry. Leonard Masonry proudly serves as a trusted masonry specialty contractor, design build partner, and self-perform specialist. Recognized for its fine craftsmanship and on-time work delivery within budget, Leonard Masonry is extremely experienced in all stonework and masonry construction design installation. And we do have Tony Stahlschmidt from Leonard Masonry here at the bar. Tony, would you like to say a few words?
Well, I just want to say that, and happy to see many faces here to enjoy the day.
Fantastic. We appreciate you. Thank you for sponsoring. And today's speaker is David Biggs. He's a PESE with Biggs Consulting Engineering, Saratoga Springs, New York. He specializes in forensic engineering, historic restoration, masonry design, and the development of new masonry products and standards. He lectures for the European Advanced Masonry Master's Program on Historic Construction and is an honorary associate professor for the University of Auckland, New Zealand. He is a distinguished member of the American Society of Civil Engineers and an honorary member of the Masonry Society. David has been a lecturer for MISL for over 20 years. We were discussing that earlier. I think it's more like 30. But please welcome Mr. Biggs.
Well, thank you very much. Thank you, Margie. Before we start, how many engineers? Wow, good. Okay, so I think it looks pretty balanced. I'm hoping that this is something you'll find useful. It's a program I've wanted to put together for quite a while on arches, and if you know, it's a huge topic. We could go on for days, but I'm going to give you the short version of it here for the next hour or so. I like it because arches are just something that are so aesthetic and so functional. It all goes together. And the good part about it is, if you know arch theory, it all began graphically. You know, stress strains and analysis and calculations were not a big part of this, and it still doesn't have to be. And I'm going to show you some examples of where that comes from. The definition, let me get a laser pointer. Definition of an arch is up here, but it's very interesting when you turn to something and it says the definition of an arch is it resembles an arch. You know, it kind of says it. Everybody kind of knows what it is, right? But I look at it that arches really take their examples from nature, and these are a couple examples. I like to say that what I've shown you from all the photographs that are in this presentation, almost every one is mine. And it's funny, the 2 left ones are in the United States, and I haven't been to either one of those, so those are not mine. The other one is off the island of Capri in Italy. That was a picture taken just before I was on a boat going through it. But nature gives us our examples, and then we have the man-made. We copy nature for our structures in many forms, but arches are certainly distinctive. And I had to throw in the St. Louis arch here because this was the inspiration for my first job outside of college. I went to work for the company that designed the erection scheme for this. And my incentive for doing that was, if they're that creative, I want to be in that company. And I did get the job, and I enjoyed it very much. Here I'm going to show you some very distinctive examples of masonry arches. You know, there are many, and some of them you're going to say, really, that's an arch? But yes, these are all different examples of arches. The Romans really brought arch technology to the forefront. It had been done many times before, but the Romans were really big at it. And their key one was primarily the semicircular arch. Okay? The Moors had their variation. So does that look like an arch to you? Well, theoretically, it can be an arch, but it just doesn't seem to fit the pattern, but it is there. And then we have the case of where the Arabs started to come up with theirs as well. Um, there are a few surprising shapes. This flower-shaped one, you don't see too many of those, but if you can put your imagination together, you see a semicircular arch and you could follow the outside of the flower here, that if you have enough thickness over and above it, it does really translate pretty much into a semicircular. There are a few surprising forms, and these two, we don't often think of arches having dissimilar heights here, but I'm going to show you later on where you can actually look at these and see these in different forms. And I'm going to show you some examples of that as we go forward, and how in some cases they create a problem or they create a solution. The arches have been used since 4000 BC, at least 4000 BC. It may have even been earlier, but that's what we have. And like I said, their popularity really rose with the Romans in the 4th century. We have many examples, and I'm going to kind of take you through time to show some of these examples. And you may say, it didn't change much in thousands of years, but that's the beauty of the arch, is the way it functions. So this is the oldest one that we know of. It's still functioning today. It's a stone arch bridge. And it looks pretty crude, right? But it works. And here's one of the first things we'll talk about. Is a key element to many of these is a keystone. And you can see it built into this with the shown state. Now, did they do this? Did they knowingly know that you got to put a keystone in there, or did it just keep falling down until they put something in there like that? We don't know for sure, but it certainly does work. We recognize the Roman Colosseum. Romans used arches structurally in their public structures and aqueducts. The Colosseum actually is not fully masonry, so I got to take that back, but it is Roman concrete. So there's an inner core, which is the Roman concrete, and it's faced with either a brick or a stone. But they used this everywhere. Not that every structure they had used interior Roman concrete, but unless you really dissect the structure, you don't always know if the Roman concrete was behind it. As I said, we're going to go up through time here, these are some photos taken from Ephesus. It's now located in modern-day Turkey. This dates back to 500 BC, and legend says it was founded by Amazons. You know, we mostly assume Amazons from South America, but here it is. They were said to have founded this city in what is now Turkey. Since then, it has been ruled by Ionians, the Greeks, the Persians, and the Romans, and today it's in modern Turkey. The construction of every culture featured arches, and this is no different. In this case, you look at the left arch over here, and you see a large pediment on the side, because one key feature of all arches is they have a horizontal thrust. They want to push outward to keep from spreading. And yet over here you see, which is a fairly slender for a big structure, to have some mass coming down from the pediment up here, and that mass actually provides the stability for that pier. Whereas the one on the right looks much more delicate. What we're missing here is all the pediment structure that was above it that provided more weight, but apparently there still is enough weight here to keep the horizontal thrust on this, that these have survived thousands of years of earthquakes, and while you can't always tell, some of these have been partially rebuilt in modern times. You've heard of Pompeii. So it was destroyed back in the 1st century AD by Mount Vesuvius, a volcanic eruption. And there's so many pictures to get from this, but I just picked a couple of the arches here because these were survivors of all the volcanic explosion that happened. Pompeii was bombarded by volcanic debris. That first did a major part of the destruction, and then the lava came through and continued that. Well, the next day that you don't always hear about is there were very hot gases that came through the city as well and put the final destruction to it. It's interesting to note how many still survive today. These are not restored pictures here. These are the ones that have simply had all the lava and everything excavated. A city that you don't hear about so much, it was to the northwest of Pompeii. So while the first explosions that came from Pompeii rained down volcanic debris onto Pompeii, that debris did not blow to the northwest of Vesuvius. So this Herculaneum had a little bit of a time period where it knew it was coming. It knew something was coming. It just didn't get the immediate debris on it. And so what it finally got was a lot of fine ash and hot gases. And what it did was, this is the excavated pictures. There was 70 to 80 feet of ash that covered this over. So it took years to excavate it out. And the structures that were underneath were in much better shape because it didn't get hit with the debris the way Pompeii did. A lot of these had wooden, heavy timber lintels for the masonry openings, the more rectangular openings. The ones you see here, I've shown, of course, the arches, but the rectangular ones were wood, and they were carbonized by the heat of the hot gases that came through, because it was about 900 degrees Fahrenheit, and a lot of those timbers are still there, but they have been supplemented with some extra reinforcement to keep them go through. But the arches themselves, this is the original construction. You're not looking at any reconstruction here. You're just looking at the removal of all the ash material. As mentioned, the Romans, they were prolific builders. And if you look at their construction, a lot of it was not very aesthetic. You know, it was very utilitarian. They were doing buildings, of course, but they did a lot of aqueducts. The one on the left here goes back to the 4th century in Istanbul. Very beautiful aqueduct. And the one I like about on the right, again, is taken from the 1st century of Ephesus. And what you'll see here is, this is very common. The Roman brick quite often is very thin, sometimes only about 2 inches or less of thickness. And you can see the very thick mortar joints here. And you'll find this in many of their buildings, but it really is prominent because with the arching action, the joints become even thicker. This is a picture of the tallest bridge, so to speak, the aqueduct, with the tallest one that the Romans ever did build. It's over 2,000 years old, and it still remains. This kind of brings me back to a story years ago. I was asked to take a look at a building near Buffalo, New York, and they said they wanted to tear it down to build a new building. And I asked, after looking at it, the brick was just in wonderful shape, and the architect had told the owner that it's over 100 years old, so you don't know how long it was going to last. So when you see things, pictures like this, you wonder how could anybody think that at all. There's no doubt there are structural arches here in this picture. And again, I'm just emphasizing the semicircular nature of what the Romans used. So that if you see what you think is Roman construction as semicircular, you're pretty much right, the Romans did it. This is down in Mera. This is now in the southwest of modern day Turkey. And there are a lot of Colosseums, you know. We think of the Roman Colosseum only being in Rome, but they built Colosseums all over here. And this is all part of the complex that is there. Well, throughout Europe, you know, you see we just jumped here to the 1300s. So we're in the medieval ages. In Europe, Romans weren't the only ones building arches, so Europe pretty much adopted the arch here. And they use them for all types of structures. So here we see a monument on the inside, but now You're getting away from the Roman construction. It's starting to take on more of an architectural appearance, and you see the pointed nature of this. And 1300s, this still remains. It has not been restored. It has simply been maintained. And the maintenance is pretty minor. This is all about keeping the roof intact on top of these structures. So it's a very interesting, and this Guimarães is a very small historical town. This is where Portugal was, the historical founding of Portugal was in this city, and there's a number of these throughout the small city. This is also another one saying, this is going to the 1300s. This is in Germany. And again, what do we see? We're getting away from the semicircle, and now we're getting more of it's circular in nature, but it's not semicircular. So what this does for them is they've learned that it has a different aesthetic to it. It opens up, you get the opening here for the waterway. But the key thing is that it leaves a very shallower depth of fill over top here for the roadway. If this had been a semicircle, it would have come up higher, and they would have had to raise the bridge even higher. So it's both aesthetic and it is structurally functioning. We're now up into the 1400s, and this is in Belgium. So what do we do? We're just like at the tail end of the medieval times, and we're into the Renaissance period. And what do we start to see? We see more aesthetic uses of materials than what we saw in those more utilitarian type structures of the medieval ages. And this is a town hall in Belgium. It has vaulted ceilings as well as these arches. And what you see is a building that received minor damage during World War I, but was significantly bombed during World War II. So a lot of this has been repaired, and those repairs were not completed even until 1983. But it's a spectacular building, and if you've been to Belgium, you've probably seen this in this type of construction in many cities. Here's a fascinating structure, and that everybody knows you never put a joint right in the middle of an opening, right? We're taught to think of concrete or timber beams or something like that. You would never think of doing this, but why does this work? And this goes back, this is a medieval period. It's actually a Mexican restaurant, if you can see this here. That's what it is now, but you have these two stones with the joint right in the middle. So how does this actually work? Well, it's very similar. With the joint being there, you would think it would just kind of fall down, but this actually, each side of it works like a buttress to an arch. And what happens is this is actually providing lateral support in the blue here, and it's actually created its own arch. It doesn't look like a circular arch, but there's a pathway for the compression to go through. So as long as it stays in compression here and it's buttressed on the side, this is working as an arch. And most people would see that and not think arch, but it actually has been used in many other places too. These are three medieval arches that I really like to point out because they have three different ways of dealing with it. The interesting thing is each one has a stone lintel over the top, okay? They all have that, but then they have three different ways of keeping the weight off of that. When you have a stone lintel, that lintel is working like a beam, and in bending, it goes into tension in the bottom, and you can have your chance of cracking the stone. But in these three cases, this one has what we call a relieving arch over the top, and then on the second one, again, it's looking like a relieving arch, that this arches and it kind of forces the load away, so it takes stress off of that stone lintel. And then we have two side by side. So that's a pretty amazing. What seemed to be a very small stone feature is really acting very structural and functioning. Here's another relieving arch, which from your handouts, I've added in the arrows here just to show that this not only has the stone lintel, it has the joint in the middle. So this is like one of those previous stone lintels where, it, imagine that had cracked in the middle, and the relieving angle, relieving arches are spreading it over the top. This one was built with a joint in top of it, but it's not flexing here because this relieving arch is just big enough to get the load to spread out and come down through the pier. So there is little to no load right here in the middle. And that's pretty amazing. And this has shown up in many different ways. Here we're looking at the 12th century. The one on the left is in Portugal, the one on the right is in Egypt. And I got kind of hooked on this topic by the one on the right here. I was at this site in 2007, I think it was. But I was just at Portugal last year and found this, but they're really doing the same thing. Here is a shallow, very shallow arch because there's not much weight coming on it, spreading the load over top of a lintel down here. And then here in Egypt, you know, we see the stone has actually been cut away to basically create an arch to the bottom to it, so it spreads over top of this. But what do we find? We don't find any cracking in the stone lintels. We don't find any distress in this. So very well done, but none of this was engineered. This was what builders knew how to do and how to distribute load. As these arches developed, they became much more artistic in their appearance. You know, we start seeing the vaulted ceilings, but they also realized that you can't always get these massive weights to stabilize the arches from spreading. So they started going to tie rods. And this building is in Turkey, these two buildings, and they both have the tie rods. And it's very important on the corners to have this outward truss controlled so that it really helps the outward one at most. The interior ones, we don't really need this. This is a self-stabilizing because the horizontal truss goes in both directions and stabilizes. So this is mostly done for the outside corners as well. UK years ago, well, centuries ago, realized that they are a big brick producer, and they built a lot of structures with brick, and it's unreinforced. And you can see this in a lot of their railway network is even today is still these brick structures. And so most of them have been in service, 200 years or more. It's amazing. You can see from the inset just barely here that the walls are massively thick. That really helps. But they have, for engineers in England, they have software that is used to analyze this as they increase loads on their railways or they go to repair them. So it's still a major technology that they have to maintain these, many more than what we have here in the United States. Coming a little closer to home, we always think of the Brooklyn Bridge as being the massive stone bridge that it is, but it's amazing if you're there on either side in Brooklyn or in Manhattan, you will find that they have the approachways are all masonry arch structures. It doesn't get written up very much, but it is a major part of this. Back in 1995, I was consulting on this for the New York City Department of Transportation because an engineer said they needed to shut down the bridge because these arches were overloaded under dead weight, under their own weight. You know, it only been functioning for 100 years, and nothing had fallen actually. But his analysis said that it was going to possibly collapse. And we went through it and found out that he had used a computer program and just got all the input wrong. And all the problems he was seeing was really just water leaking down through the roadway that was getting down through. So they needed to take care of the roadway, and the masonry was fine. So I always laugh at that, to shut down such a major bridge over that. This is in Florida. We're looking at the late 1800s. And I just saw this, just even a few months ago. I went to see this in St. Augustine. And it's really quite stunning. You know, this facade is brick and terracotta. The structure underneath it is concrete, and while it's not 100% masonry, certainly the arches are just fantastic on this. And they are, I believe it's an anchored system back to it, but the facing is still doing the arching action. Uh, Come a little bit closer to our time period, this is modern brick veneer on a cavity wall construction. So the thought had always been that, you know, when we went to cavity wall construction, the cavity makes that veneer so thin that you can't use arches, and that's just not so. It just needs to be looked at closer. In this case, you can see that the horizontal thrust that happens, it's kicking out here, and I kind of cut off the picture, but this is the end of the building. So it's a matter of determining what is the horizontal force here so that you don't get a shear going through the veneer. Now, the masonry code will tell you that brick veneer is non-structural. You don't have to be worried about the F prime M or things like that. On this, you've got to be thinking of the material as structural too, because there are shear stresses that are taking place here that you usually don't think about in an anchored veneer. But this has been around. I did this building back in probably the late 80s and early 90s. So it's worked out quite well. So that's a bit of the art to it. Now I want to kind of show you a little bit of the science to all of this. Um, you know, I'll skip through this quickly, but most people know what the pieces of an arch are. The crown, the intradose is the lower level to it, the extradose is it, and the keystone is there. And then we call the voussoirs the stones themselves. You can find this in all textbooks, but here's the graphic, and this is actually a two span arch, masonry arch bridge. This is all granite that was restored in 1985. The state of New York was going to condemn this and put in a concrete bridge because they didn't know how to analyze masonry. And the historic people wouldn't let them tear it down until they had it validated by an engineer who knew masonry, and I didn't give the I didn't give the validation, and it still looks terrific today. This is, you know, this is 40 years after the restoration. It's still in great shape. But when we talk about structure on arches, you know, we usually think of hinges. There are two hinged arches where the bases pivot and rotate, and there's a three hinged arch at the top. Now, these two arches are generally used in steel structures, in timber structures, but not so much in masonry. We don't tend to build in hinges. Now, the key thing about it is arches are stable as long as there are less than or equal to three hinges. This is a stable structure. It's actually, for engineers, is actually determinate too because of that hinge. This is indeterminate, but it's still two hinges and it's stable. So that's a very important fact. When you go out and look at arches and you start looking at cracks and positions of them, things like that, if you have 3 points in that or cracks, it's stable. If you look at more than that, that's when you run. The masonry arches tend to be fixed at the base. You know, it's built in tight at the bottom, and it's built continuous all the way through. So this is what we call a fixed arch, and that's what masonry has. I throw this in too because it's also typical of masonry, historic masonry construction, where the corbelled arch is used to actually build this. So remember that picture because I'll show you some of that later on. And this here it is right here. I forgot. The next one is a corbelled arch showing a historic one. It looks like it's on the verge of collapse, but you can see it's still functioning. There's still enough contact here that it's still working as an arch. But this is more the typical that we see. This is from a Roman bath. This is underneath. The bathhouse would have been up above, and the steam heat and all of it would have been down below here, radiating up into the bath. But you see the pediment, the abutment here is very stout. It takes the horizontal thrust. and it arches through, but there is no built-in hinges on this. So if we want to design this, we're using the science of masonry and the science of arches. What do we have to know? We have to choose a configuration. So if you're designing it or if you're analyzing it, you got to establish what is it. Is it a fixed arch, which it usually is in masonry, or is it one of the others? Then you also have to look at what's the structural thickness to it. Those stones. Somebody had to pick out how thick of a stone are we going to use there. You also have to know what loads are coming down on it. If we have a veneer on a building, it's mostly the weight of the veneer that is over top of the arch, but if it's a structural arch in some way, you got to know all the other loads that are on it. And then as we look at modern reinforcement, modern arches, we do look to reinforcement. And I'm going to show you a case study on that. But one of the key things here, like I've said before, is that we have to keep these abutments from spreading. If they start to spread, we then start losing our stability, because that's when the hinges will start. And I'll show you that in a later slide. Now, if you remember the configurations of the arches, I showed you two where it did not have equal abutments here. They were at different levels, right? So that is actually a case, if you took an arch and say you had foundation settlement on one of them, you could conceivably have it settle and start to crack. But if you fill in those cracks after it's settled and you stop the settlement, it would restabilize as a different configuration arch. Doesn't sound right, that it cracks, it moves, you stabilize it, and it keeps going on. But I'm going to show you an example of that as we go forward. Now, this is where the artistic matches up with the structure, because how do you determine what the correct shape of an arch should be to carry the loads? And in this case, I'm showing a uniform load. So what we see here is a chain, and you hold two ends to it, you make it as long as you want, and it will change configuration. It could be shallow, it could be deep. This one shows this height, and here's a chain over here. So when you have that shape, it naturally forms what's called a catenary. A catenary geometrically is very similar, but not exact to a parabola. But when we design, most times people will lay out an arch with a parabola formula because it's easier than tracing a catenary. But here we see. So how do you take this, which this is chain, it's held totally in tension. Well, if you simply took that and turned it upside down, you've really got an arch. That's your ideal shape for an arch that has a uniform load sitting on top of it. And there's no calculations here, right? It's all just done by shapes and graphics. And that's pretty cool to see that. Now, here's a semicircular arch with a uniform loading on it. So what do we see? We see an arch with a certain thickness, and superimposed on it is one of those parabolas, okay? And so on the parabola, wherever it touches the face of the arch, that creates a hinge. This is in compression, and the hinge is going into tension on the outside. The theory in arch is that it can't take tension. It only can take compression if it's unreinforced. So this is a historic arch, semicircular, and this catenary or parabola, as it goes through there, tells you that at this point, if this is the thrust of compression going through here, because that's what it is, that shape that we created with the upside down chain means that this line is in compression. Okay, and if that's in compression and we have tension out here, we have three hinges. And what did I say? Three hinges, and it's stable. So this is at the point where it is still stable, though cracked. If I came in and repointed this crack and these, I've just strengthened it again back to its original construction. So it's a matter of the strengthening to this is nothing more than filling the joints. Whereas what you see over here, in this case, if the catenary was done in this configuration, you can see that what did it do? It opened up 4 joints. And those 4 joints, this is on the verge of collapse. This is at the stability point. So you can see that it all changed because that catenary was held back here. Now the key thing about an arch is, this is the same arch, okay? And if I have one catenary that I can draw in there and it doesn't create any more than 3 hinges, it's stable. Whereas if I allow this to happen, it would be unstable. But because I can draw an unstable configuration does not make it unstable. How's that? You only have to have one pathway through this. The stone doesn't know any different. It works. And as long as there is a pathway that works, it will find it and it will make it work. Does that sound odd or what? You know, so you have what seems to be like a failure point here, but as long as you have a stable point, it will go to that. Okay. Now, the one thing I haven't told you is it's in this simple theory. It assumes, again, that the stone and the joints don't take any tension. It also assumes that if these are individual stones, that they don't shear through. That is the one assumption that you have to be careful about. That if they were starting to slide, and they could slide too much, you could have a failure. But if it started to slide and restabilized itself so that it still has a reduced effective thickness where it's overlapping, you can still get that catenary still goes through it. So it's amazing structure on the flexibility it has to perform despite things. So here is that arch again, which just shows that in one cases, you know, you have 2 different versions of the catenary. You know, this one is showing coming to the outside, this one. So it's only as long as I have one version that works in there, it is stable. And with that, you can graphically determine what is the thickness of the arch. Okay, no calculations here, it's all done graphically. So here is something that if we go even further, that bridge I showed you, the 2-span bridge, this is what we used on that. It's called the 3rd rule. If you further look at the analysis and keep this catenary, so in this case, I kind of got ahead of myself. This is done with showing some point loads at different points, but it's creating a shape like that catenary in here that we have to modify. And we're staying in the middle third. So this is what we're seeing here is the thickness of the stones. This is one thickness, but in here it's broken down into thirds. So we're keeping the entire compression in the middle third. And if you do that, it eliminates tension on the exterior. For the engineers out there, these are the kern points. If you stay within the kern points of compression of the element, it will not create any tension on the exterior. It was even the exterior, you know, you'd have high compression on one and low compression on the other one, but you won't have tension at all. And that is a very powerful tool. This is just to show you a comparison of a semicircular arch to a parabolic shaped arch. Now, if you remember, the parabola is this shape over here is very close to a catenary. So when on this one, semicircular, you're trying to fit a catenary into it to make it stable. And you'll see there's a ratio here of the thickness to the ratio you can get, and look how much thinner it is when your shape that you are creating of the arch is closely matched to that natural catenary. The thickness goes down because it just keeps it in almost 100% compression. So if these are stable, what are we looking at here? Well, this shows this point where I've got 1, 2, 3, 4, 5 hinges. This is collapse. This is on the collapse because this thickness is right at the point where it's becoming unstable. So if I were to pick an arch and choose a thickness that exceeded this ratio, a little bit larger, I would get back to moving the thrust point inward and creating a more stable arch. So these 4 or 5 hinges would revert back to possibly 3, but it would still be stable. Whereas over here you can see this again, this is right at the collapse point where we've got 5 hinges happening. Okay, so graphically we can do this. Analytically, these numbers are known for uniformly load. You know, it gives you an idea of what a thickness would be on any of these arches. Well, the reality is that most arches aren't uniformly loaded. There are point loads, something's going on, there's something it's supporting special. And so in that, rather than creating a uniformly catenary on the thing, this is what's called a funicular configuration, where it's still got, we're looking at a hinge down here and here. So this is taking we're assuming our fixed arch, two hinges have formed by cracking. And this funicular arch shows that if this was built, it's almost like a truss. If these were built, that these elements would be in complete compression. That's what it's looking like. And these point loads are coming down. So that if we were to match that up with a real arch, say architecturally this is the arch you want. You want this shape, but this is where the loads are coming in. We now start to blend them together, okay? So we have the theoretical preferred aesthetic arch, yet we have the stable funicular arch here. So what happens? What happens is that this is where we're introducing bending into the arch. The bending is due to the load and the differential between the two arches. So now we're getting into some computations. You know, the historic ones weren't done this way. A lot of them were done with trial and error. If it didn't work, you made it thicker. That's about what they did. But today, we can use this to create modern arches that are reinforced, because the reinforcement is put in to handle the bending and the shear forces created by these two theoretically different profiles of the arches. Move on here. So I'm going to show you an example. This is nearby. This is a chapel, St. Louis University, where they came to the structural coalition here at the Institute and asked for assistance in looking at this as a structural masonry system. So what it is, it's basically 2 intersecting arches. It has a sloped roof on it all the way around. It's octagonal in shape, and it has a spire on the top. Anybody seen this? Did anybody design it? Okay, I put the credits here of who did this. This was done by John Smith Masonry. I just want to show you how this theory that we've been talking about can be put to use. So here's the arch concept. Now remember, there's 2 arches. They're going across the diagonal, so they intersect. But there's 2 of them, and they have to take the point load of the spire. They have to take the point load of the intersecting arch, where they share some of that. But what was not done in historic times was to sit and really think about the wind and the earthquake. So this is a fairly high seismic category, so you got to take lateral load into it. So this is not only taking in if we drew in the funicular and the uniform catenary in here, it certainly would fit in here. I have no doubt it will fit in. But it's these other loads, from the point loads and the lateral loads, that cause bending in this. So what was done is this was treated as a reinforced arch. It's a masonry beam, basically, that is faced as brick. And here is just some sketches that came out of this. So there's a brick along the sides and the bottom. The interior is reinforced with masonry reinforcement and grout, and it is designed for the bending forces that happen through these lateral forces. This is an actual shop drawing that was done of the reinforcement. So the Institute here helped the designers in looking at how to place the reinforcement and make this all work. And then they took off and ran with it. So here you can see the reinforcement. What I did is I blocked out the foundation because it's very important. What didn't show up on the shop drawings was the piers are dialed down into the footing. Well, not the piers, but the corners are treated like piers that go into the footing. And then a horizontal tie rods are used here to take the thrust. So that's all below the floor that you don't see, but it's functioning just like the simple arches that were showed. Here are some construction photos. This one just showing the formwork being in place before it was done. And then that section I just showed you, the cutaway of the reinforcement going into the edge here, and it all going up. Once it was built and became stable, the formwork all came out. Here's the formwork just before it was deshored, and this was in 2022. And this, I don't have a picture of the final because you lose some of the arches because they're inside here, but the arches are both done. And then the exterior part of the octagon was filled in with light gauge framing, and the roofing had to go on and everything. But it's very similar. I mean, you start out with everything just with the simple theory of arches and then come up with the that Eddy's theorem of how much moment and shear do I have to take, and that is the reinforcement. Very simple structure, actually. A little more difficult to build because of the curves, but that's the fun about it. So let's take some look at some restorations. This is a cathedral in Portugal from the 1200s. I like this because this is the side aisle to the nave. So the main opening in the cathedral is over here, and these are side aisles, and there's one on either side. And you can see the arches that are here. Well, I want to blow that up for you so that you can see that it's distorted. This does not look like a semicircle or any other of the normal shapes. It is because what happened is the walls over time after it was built pushed outwards and settled. So in theory, what we're looking at is this. This is kind of exaggerated, but that's one of the sketches I gave you of the different configurations of it's high over on the left and it's lower on this. So it's not your typical arch. So how was this fixed? It was a simple, there were cracks that developed here because of this settlement. They simply filled it. That was the whole strengthening and restoration. They understood that arches could be made stable again. The key was they stopped the settlement. That was the big engineering on this, was to stabilize the foundation so the walls were not settling anymore, but they basically just filled the joints where any cracks were. And now it's back to being, instead of a semicircular arch, it is this distorted arch, but it is stable again. You don't get that with many structures where they're simply fixing it that easy. This is in Ghent. Here you see, remember I showed you the other one, there's arches. You look at this and you see an arch. That's not what I see. What I see is a small arch, a small arch, a small arch. I see all these pieces. That's the way it's functioning. Having the vertical support here changes it significantly. So this is not a full arch anymore, it is pieces. And these pieces are short enough that they are forming the strength and the stability there. Here's another one where you can see a large arch. But again, I don't see a large arch, I see pieces. And in this case, you see a short arch here and a longer arch here. And it's that longer arch that has had the problems. This is where the cracking is taking place. I was there last year in February working on this with them, and this picture was taken before the scaffolding was put up, but the cracks are very prominent on this. And this was really leading to a possible collapse because what we're seeing is the arches are not supposed to shear through here. this all drops down, they're going to lose a good bit of it. So the picture was taken before the restoration was planned, but this had to be fixed because this was actually bearing down on the mullions of the glass. So this was going to be stabilized by putting a reinforcement in the bed joints up here and making this more into a structural beam. So I haven't talked to him, but I believe it's been completed. And another cathedral in Porto, this is again in Portugal, you again see the pointed arch. Again, I see 3 different pieces. In this case, not like the last one had a long center arch, this was short and that was stable, but these longer ones actually are where the problems occurred. This actually started to not have enough thickness here that the arch couldn't function as that short arch. And this actually, because it was small, these were actually rebuilt and reconstructed, but basically back to the original. Here we're in the United States, 16-sided building on the National Register. One night, one of these piers between the arches, it's 16-sided, and one of these blew out, came out of the blue. There was a little bit of mortar deterioration, but it blew out. And it had to go in and be filled in quickly and shored up to keep it from pushing out. It all turned out to be an issue that the 16 sides of this, each one of those arches was pushing outward. The thrust of each of the arches, if they're in plane, they buttress each other. But if they're on an angle, they have an outward thrust, and that outward thrust is what caused the weakness of the arch. And on the one where it failed, there happened to be a chimney built in to the as well, so it wasn't a full thickness, and that pushing out action is what caused it to come down. There is sometimes where arching action is beneficial. This is from the World Trade Center. Again, I was there for that, and this is the Verizon building north of the North Tower. It was the arching action of masonry. These are transitional buildings, steel frame buildings with a masonry veneer, but it arched to keep all of this from collapsing up above. It was not intentional, it was not designed, but it worked well. What you see over here is the Pentagon. When the building was hit by a plane, the debris of the plane went through several rings. Pentagon, it's got many rings, but the debris pile blew through the bottom floor, and this was the exit point. People said that's the shape of the fuselage. No, there was no fuselage left at this point. This was just the moving debris that punctured it out, but they had no collapse. It was simply just a matter of punching this through, and it arched over the top of it. So that was a beneficial use of it. I'll finish up here with a few things on arches and involved to that, but this is from some work I've done in Iraq, and the students were asked to build things. These are made out of mud bricks, and it was just to show them how they could actually restore some of their historic structures or even rebuild some of them using understanding arch theory. So they got to build these in I won't call it a classroom setting, but it was in a site right at the building there. But then we went on to look at domes. So here's the dome that they built. And the one thing about the dome that's interesting, it's got a hole in the top. So let me explain, how do you get a hole in the top? You never cut out the top of an arch. Because what is a dome other than just a series of arches next to each other to create this dome shape? So the theory of the dome is basically, again, these are like arches going around, they're side to side. But once it starts going into 3 dimensions, the thing is that we tend to find out that if you were going up from this cutaway here, 51 degrees from horizontal, at the dome there's a point where the top is in compression and the bottom is in tension. And this is overemphasized compared to that 51 degrees, but it shows that if you're down here in tension, this all wants to split at that part. Yet the top would all be in compression. So that's why you can take out the top of these openings, because in 3 dimensions, if you're missing a hole at the top, an oculus, that opening can be missing and can still get the compression to go around it. Very cool structure. This goes back to the corbelled arches. This is in Turkey. This is a 2-room structure for burials, and it's all done out of corbelled arches in the shape of a dome. So these are 2 domes. If you can't tell, these are actually 2 of them side by side. These were excavated in 1955, and if you looked at this, you would have thought they were built yesterday. The stone is just in that good a shape. I didn't take this picture. This is in an area that was preserved. I was there because one of these had been bulldozed. They have a problem with robbers. And somebody found a site and they started to bulldoze it to rob it if there's anything there left. And they took off the top. So the bulldozer actually dug out and really messed it up. And we were there trying to evaluate whether or not they were going to restore it or simply just document it and bury it. And that's what they did. They had enough of these that they didn't want another one for display. You do know of the Pantheon, so here we are in Rome. Again, this is not masonry, this is unreinforced concrete, but I show this mainly just to emphasize that oculus. So here you see they used a coffered structure on the underside. It adds, it takes away weight, but you can see where they understood that the compression was very high at the top because of the opening, that they made it solid. Very smart. They understood how these things all work. The other thing they did was they changed the thickness of the roof. Here's a cross section showing the thickness, and it got thicker toward the bottom. Remember, at the bottom, in tension. They also put in these ring steps where they used it to kind of form like hoops going around it to stabilize it too. Did it stop it from cracking? No. It did crack, but it is stable and it's there. Let's see, I got a few more slides. Can I keep going? This is the Hagia Sophia in Istanbul from the 500 AD. This was built as a mosque. It changed to a church, and then in 2020 it was made back into a mosque again. But it's called a pendantive dome. That means it's a circular dome sitting on 4 corners of a square, so you have a lot of open area, and then there's smaller domes underneath too. This has gone through numerous earthquakes and damages, and it has been restored mostly by either repointing cracks or putting in some hoops. Again, the spreading action caused by the dome at the bottom is what they needed. This is probably one of the most famous domes of all time, Brunelleschi's dome. Not an architect, he was not an engineer, he was just a smart guy, and he came up with a way to build this. This is in Florence, and what they did is they built the cathedral here up to this point. And there it sat for 100 years. 100 years with no roof on it, because they couldn't figure out how to build the dome. And they had a competition, and this fella who hadn't designed a real building before comes along, and he's got the way to do it. And they did it. They built this, and his key to doing was he figured how to build this without any scaffolding. If they had put scaffolding and shoring underneath this, which most of them had, it would have taken a small forest to do that, and the expense, and he figured out how to do it without. If you ever get a chance, it's a wonderful place to go. This is St. Peter's Basilica in Rome from the 1590. It cracked, and in 1748, it was the first time somebody came up with an analysis to understand the cracking. So what I showed you about the cracking at 51 degrees, that was all worked out analytically, but it was nearly 200 years before they could figure out how to analyze it. Imagine getting a job where you say, well, I can't do any calculations really, but I think it'll stand. And that's a lot of how these structures were done. We go back to the end here, and the Iraqi Institute, this is the students building a barrel vault. A barrel vault is really nothing more than a series of arches side by side, so it works under the same principle. There are many examples throughout Europe and here in the States where these vaults are used, and some of them have tie rods, and some of them are treated just as simply as arches, but it's all about horizontal thrust. So there are many to this. Kind of ran you through an awful lot of things here, but here just shows some of the work that, this is some work we're doing in Portugal about strengthening vaults. You know, I showed you the sketch. It showed where the hinges are. And a lot of times those hinges or the cracks are open on the inside, as you see here. So the idea is, how do you strengthen this? Because if this is an exposed inside, how can you strengthen this if you really only have access to the exterior? And that's happening a lot now. We're looking at ways of doing this. This uses FRP to strengthen the outside. And the idea is to take enough added compression over top of that crack that it's not as bad as cracking on the inside. The other way is to go in and use to thicken this. Why does the hinge form? It forms mainly because the vault or the arches are too thin. If we can't get that compression zone within the thickness, so you simply add more thickness to it and move that compression line in further. That's a major strengthening thing, but they're doing things like this where they say they don't want to add more weight and they want to keep it as thin as possible. So the FRP, it helps with all of that. So I didn't credit everything in here. Again, most of the photos were mine, but I give you some good references if you ever want to read anything about some of the things other than the book that's going to be handed out in the raffle here. These are some excellent ones about this, and I give some credits, and there's some of the tech notes from the BIA. So this is something you can take a look at on your own. So with that, nobody stopped me. Nobody asked me any questions. But if you have questions, I will be here afterwards if you want to talk about it. But I really want to thank Leonard Masonry again for supporting this. These are great programs. I'm proud to be a small part of this wonderful seminar program, and maybe I'll even see you again soon.
All right, thank you. Thank you.